So let's try an application problem. Here we have a cup of milk is chilled to 50 degrees Fahrenheit in the refrigerator, and then it's taken out into a room which is 80 degrees Fahrenheit. After about 4 minutes, it's warmed to about 60 degrees Fahrenheit. And we want to know approximately when will the temperature reach 70 degrees Fahrenheit. Now, this is an example of Newton's law of cooling or heating, depending on whether or not the temperature is going one way or the other, where essentially Newton would state that the rate of change in temperature is proportional to the difference in the temperature and its actual medium. Okay, so if I have some object, then the rate of change in the temperature of that object is going to be proportional to the difference in the temperature and the temperature of the surrounding medium. And it should be clear that if we drop that symbol of proportionality, we can replace it with an equal sign. And here, t prime, or t, is a function of time. So I guess I could write t prime as a function of time. And I'm going to drop the proportional symbol, write the equal sign, and then I'll include some constant of proportionality. All right, so k t minus tm. And if I distribute the k, I get k t, I guess I could put the t of t, the time dependence, minus k tm. Okay, so any one of these would be, I guess, a valid treatment for Newton's law of heating or cooling. So let's go ahead and pick out some information here. We said that a cup of milk is chilled to 50 degrees Fahrenheit in the refrigerator, and then it's taken out, which seems that the temperature at time t equals 0 is going to be 50 degrees. And I'll drop the Fahrenheit, the F, because it's clear that any temperature I find is probably going to be in Fahrenheit, and any time that I find will be in minutes. And so it's taken out into a room which is 80 degrees Fahrenheit. So it seems like the temperature of the surrounding medium, which would be the room, which kind of, I guess, would serve as like an infinite reservoir for, I guess, if you had a hot object, it would get rid of its heat in that reservoir. Or here, I guess the environment would act on the cup of milk. So the temperature of medium, or the surrounding medium, is 80 degrees Fahrenheit. And we also see that after 4 minutes, so the temperature after t equals 4 minutes, it's going to be 60 degrees Fahrenheit. So we have a lot of information, and we'll see why. I mean, there's a reason why we sort of need that that other state of the system imposed, not just the initial state, but maybe some later state as well. All right, so if we take, let's go ahead and take, say, this guy, and I'll just rewrite it. So I get t prime, and I'll drop the time dependence. In fact, let's write it as k times t minus tm. Now at this point, I really could write the t prime as dt by dt, the rate of change in temperature with respect to time. Then I could divide by t minus tm, and then multiply both sides by dt, and treat this as a separable problem. Okay, so if as a separable problem, I write this as, say, dt over t minus tm is equal to k dt. And that's still subjected to the same conditions. But I want to go ahead and treat this as a linear problem, because it turns out that if I take a look at this, I could write this as t prime, and if I bring the kt over, I get a minus, say, kt is equal to a negative k tm. And that ktm is really just a constant, so it doesn't necessarily have to be a function of time. And this is clearly linear. So if I go back to my definition for first order linear ODEs, I'd have like an A1 of, in this case, t, which would equal to 1. And then my constant would be this minus k. I'm going to go ahead and solve it in a linear sense. Though it doesn't really matter. If you want, you can take the separable case and begin to integrate. Here you get the kt plus c here, and over here you get the natural log of t minus tm, but I want to go ahead and take a look at this in a linear sense. So Since it's linear, I can clearly identify, it's kind of like my P of X, except now it's like a P of T, if you will. And I write my integrating factor as e to the integral of P of T, so it's like a minus K. Minus K is really a constant, and I'm integrating with respect to time, since that's my independent variable. And here I get e to the minus kt is my integrating factor. And if I multiply this through the ODE, I know that on the left hand side I'll get the exact differential d by dt of the function times the integrating factor. We'll kind of skip some steps here, but after you do enough of these, you start to realize that you'll set up the product rule, and it all boils down to you just taking the derivative of the function and the integrating factor. The key mistake not to make, I guess, is that you have to make sure that you multiply your integrating factor times the right hand side, which skipping steps could easily cost you, because it's an easy mistake to make. Okay, so now if I want to just integrate both sides with respect to time, put a little dt here, integrate here, add a little dt. Again, the first fundamental theorem of calculus tells me that I have t of t times e to the minus kt is equal to, so now here I have a minus k times tm, which is just a constant. And if I integrate e to the minus kt, I know that if I integrate e to the alpha t, I get 1 over alpha e to the alpha t. So here I'll get 1 over, say, negative k, okay, or negative, say, 1 over k e to the minus kt. And in this case, I'll still have to add a constant of integration. And again, if you wanted to distribute the minus ktm to the c, it's going to be a constant anyway. K is a constant, tm, which is 80, it's just another constant. So I'll just bundle it all into the constant c. So here I have a minus k, here I have a minus, and then I have a k. So it seems like now I have t of t is equal to, so I have, I guess if I multiply both sides by e to the kt, I'll just get a Tm here, the temperature of the medium, because e to the kt times e to the minus kt will give me 1 plus c e to the kt. So again, we have a basic model. It's first a single family parameter of curves, and it's really just an algebra equation now. We can apply our condition to find c. So if I apply my initial condition, I get that here, and I have that 50 for the temperature occurs when I have a time of 0, so my Tm, of course, is known, that's 80, plus c, e to the 0 is just 1, so I get that c is going to equal to 50 minus 80, which will give me a negative 30. So let's go ahead and put that back in our model. And now we have, I guess, a more refined model, if you will, because we have now t of t is equal to, Tm is 80 plus c, that's going to be a minus 30 e to the kt. And so now you sort of see why we needed that other state of the system imposed, the t at time t is equal to 4 equal to 60, because if I plug in 60 for t and then 4 for little t, I'm just left with an equation in k. And if I solve this, and this is just a few algebra strokes later, you should get 1/4 the natural log of 2/3. So now that I know k, I really have a complete algebra model now. 80 minus 30e. I guess I'll write all this out. So I have, alright, this is t over 4 natural log 2/3. And so this is all algebra now. So for any time t, I should be able to predict the temperature, or I should be able to tell you at which time this milk will reach a certain temperature. Well, it so happens that we're asked, when will the temperature reach 70 degrees? So I just plug in 70 for t equals 80 minus 30 e to the little t over 4 natural log of 2/3. And after some manipulation later, you should find that the time is going to be exactly equal to 4 times the natural log of 1/3. Of course, you can take the natural log of 1 minus the natural log of 3. You get a negative ln 3. And then at the bottom, I have a natural log of 2/3. Again, you do ln 2 minus ln 3, which again is also going to be negative. So I have a negative over a negative. That'll give me a positive time. And I have that that's roughly 10.8 minutes. So to answer the question, in 10.8 minutes, I should expect the milk to reach 70 degrees Fahrenheit.